Welcome everybody. Welcome to CS4306 lecture 1 part 2. I have already uploaded this lecture in D12 week 01. So this is the lecture. So this is the lecture slide. You can download it from D12. Okay, so let's start. So in this lecture we will continue and the course overview and introduction to algorithm. That is the part of chapter 1 and 2 of the textbook. Okay, so this is my my contact information. Please, when you send me an email, please mention your course number at least. Okay, so again I would like to thank you, Dr. Angshu Lee, for allowing me to use her slides. So in this lecture video, I will discuss insertion sort and merge sort algorithm analysis. How do we analyze these two sorting algorithm, and how do we compare the complexity and efficiency of this of algorithm with an example of these two algorithms. Okay, so let's start. So as we know, the insertion sort and merge sort, these are two popular sorting algorithm that are used. And if you have taken our 1321 course, CSE 1321 or 1322, then you should know this. So insertion sort algorithm. So this is the pseudocode of insertion sort algorithm. So here the method name is insertion sort, and A means an array and with size n. Okay, so the normal procedure is for j equal to 2 to n, that means from the second element of this array. So what do? We initialize a key value as the aj, that means the second element of the array. So and then we do a comparison over here, and we do a swapping over here. So I will go to this in detail. So one thing is that the main difference, remember the difference between pseudocode and actual code is that in pseudocode we start with index 1. Usually index is started with array index is started with 1, but in actual program code in most of the languages we start the array index with 0. Okay, so in this algorithm, so in this sorting process, there is, we see that at least a for loop and a while condition, right? So as we go through this slide, there is an example that how insertion sort algorithm it works. For instance, these are the original data value given in a list or an array. We want to sort this list as in ascending order. Ascending order means that at the end of the sorting we will get our lowest element, smallest element at the beginning, and the highest element will go all the way end. So 2 will come in the front on the left side, and then 8 will go, or 9 will go all the way right side. Okay, so this is the process that, so initially if we have a small number of elements, then we can visualize this insertion sort algorithm very intuitively. Okay, so what it does initially, it is sorting. We see that 8 is comparing with 2 is comparing with 8, so since 2 is less than 8, so then 2 will come in the front, and then 8 will go to the next place. Okay, so then we will get a little bit modified or sorted list. So but there are many internal steps over here. So if we go through these slides, we will see how the comparison goes. So and then we will see that there are many more comparison. So how many comparison we need, actually how many elements we do have? 1 2 3 4 5 6 elements, right? So there we need 6 minus 1, 6 6 minus 1, that means 5 comparison. 1 2 3 4 5 comparison. At the end of 5 comparison we will, so here at the end of 5 comparison we will get our sorted list. Okay, so now we will analyze this sorting algorithm. Okay, so but if before I go to this analysis, let me open the sorting algorithm from our FYE, first year experience page. So it is a part of 1321, so searching and sorting algorithm. So if we open this slide, okay, so at the end we have insertion sort, right, number 4. So if we go quickly, okay, so I want to discuss how the insertion sort algorithm internally works. Okay, so there are more detail over here. So for instance, we have a very short list. Okay, so then 8 4 2 and 1. So and but at the end of our sorting process, we want to sort it in ascending order. So this will be our finding. Okay, so here we will see that this is another version of the insertion sort algorithm over here. So it's the same thing. So what happens in pseudocode format, and then in Java format, and in C# format and C++ format, we have our program code over here. Okay, so what happens in the insertion sort algorithm, that we see that, so we consider as a key this is the second element, right? So the second element as a key, and its index, it starts with 1, right? So in array, and position is 1. So we compare 8 4 with 8. Okay, and since the position is 0, so then we see that there are some internal comparison here. So some internal comparison here. So these internal comparison actually are shown here, but not in depth. What did I leave? Okay, they are shown over here. Okay, so they are shown over here. Okay. So now what is our goal? We want to analyze this algorithm. Okay, so analyze this algorithm. So in terms of what, as we discussed in our part 1 of lecture 1, that we analyze or we consider algorithms based on 2 criteria. One is the memory size, and another is running time, the time it needs to complete the algorithm, right? So since we said, although all algorithms need some memory space, but in our modern computer we have a lot of memory, that means RAM, we are not worried about memory. So we will consider running time needed to complete an algorithm. Okay, so in the so how do we analyze an algorithm? We analyze an algorithm in three contexts or three situations mainly. The worst case, that means in the bad situation, if all the data, for instance, the bad situation, that means if all the data are unorganized. Unorganized means if all the data are given in descending order, but we need to make in ascending order, so that means everything almost is unorganized, right? And then we will consider that in worst case, that means we will consider in worst, that is our worst case. Okay, and average case is that, for instance, our best case is that we may not have any need, we may not it's already sorted, we don't need to sort, we don't need to swap any elements, right? So in general that may not happen. So in average case is that we may have a few elements that are unsorted, not in position, so we need to sort those, only those elements. So but in while we analyze algorithm, we usually consider the worst case. Okay, that means we need to consider the worst the algorithm by considering that it may be what it is totally unsorted or mostly unsorted. Okay, but one thing that we will consider an algorithm for a large value. So if we have a small set of data value, that is not a factor, right? We can do it manually, or we can we don't realize the difference in our algorithm. Okay, so as we know that we discussed in our last lecture that we analyze algorithm based on the parameters. So what are the parameters? The number of variables that are used in the algorithm, we say those are parameters. So and another thing is that we will analyze our algorithm in asymptotic analysis. So if you took a math course, so discrete math course, so you will know that what is an asymptotic analysis. That is an asymptotic, that means it is the condition in very far or infinite distance. Okay, so that means we will consider a very large n. Since n is an integer number, so actually that does not have an actual infinite value, that has a very large value. So that means n tends to infinity. That means n is not an infinite number, but it's very large number. We'll consider that. Okay, so okay, and so how do we analyze an algorithm? So we have some symbols. So we use big O notation, and then omega notation, and then we use theta notation. Okay, so I will come back here. So let me see. So and then we will use the worst case method. Okay, so in mathematical conditions, so we say theta notation in algorithm analysis. So for instance, what is that? So theta is considered as a function gn of fn is a function. Okay, so think about that. It says that if there exist, okay, some positive constants like c1, c2, and n0. Okay, so we already have n is a positive number, right? And these are the constants c1, c2, and n0, such that c1 times g of n function, g is a function of n, okay, multiplied by c1 is a constant, right? c1 is a constant, and n for it will be some constant value, so this will have a value. Okay, is less than f of n, the original function. Okay, This is the f1, fn is the original function, and gn is the f1 in terms of another function. Okay, so such that c1, that is this constant time, gn is less or equal to fn, and that is again less or equal to c2, that is another constant, times gn. So for wall n after a certain n0 value, that means after a certain n, if we find so like this such a condition, okay, then we say that this is theta n. Okay, and that means, so that means this algorithm will have a boundary. So this is the lower bound, and this is the upper bound. Okay, and for all n value greater than n0, that means after a certain n value, maybe can be 30, 40, 300, something like this. Okay, and for instance like this. So if my tn is a function, okay, that is time function, is based on n equal to 3n cube plus 90n squared minus 50n plus something constant, right? So here, in order to find the complexity of this algorithm, so for instance we will consider only the shortcut, the highest term. Okay, so the dominant term, what is the dominant term over here for large n? We see that for a large n, very large n, maybe we said n tends to infinity, so this is constant, so we can skip it. So for a large term, so n cube, since it is a positive integer number n, so n cubed, n squared, and n, right? So let us see the 3. So definitely this term is the largest term. Okay, but some of may confuse, maybe this may be a largest term, because if n equal to a smaller number. Okay, so but since we are considering n as a large number, so we will consider this term, and then we don't, for large n we don't need to consider the constant, so that it comes like gt is theta n cubed. Okay, so this is the dominant term, we will consider this. Okay, so in what we see that in insertion sort algorithm, since it start with the second element, okay, so what we will do, we will see the insertion sort algorithm, it takes theta n square, this is the running time complexity. Okay, and in average case, that means we see in average case, that means if some of the elements are already sorted, then still we will consider we have to go all the way and all of the elements, right? So then still its complexity is theta n square. Okay, so the now is common question is in the insertion sort algorithm is a fast sorting algorithm. Okay, so it is actually a tricky question to answer. Actually, maybe yes, if it is n is a small number, but not always for large n. So for a large number, so there are other algorithms, right? So what is that called? The merge sort algorithm. So what is a merge sort algorithm? It merges two lists. And how? Actually, what two sublists? Actually, the a list on an array is split into two lists, two sublists, and then it merges, it compares and sort, and then merge. Okay, so computer scientists are working, still doing a lot of research to develop better and better algorithms. So far merge sort algorithm is known as one of the best sorting algorithms. So how, and now let us see how the merge sort algorithm works. So the merge sort algorithm works. This is in pseudocode format again. So it start with, this is an array, is an array, and it has elements 1 2 3 4 5 6, something like n elements. And for instance, we can consider that we have the elements that start with 1, the regular number 1 2 3 dot n. Okay, so it has n elements, right? And since it is a pseudocode, the elements, the index will start with 1. Okay, so in the behind the scene, the merge sort algorithm works recursively. So since you have taken 13 22 and data structure course, so you know that recursive algorithm, it works intuitively and in place. Okay, so and then it is the faster algorithm, okay, process. So in merge sort algorithm, what does we do? We split the original list. For instance, this is the original list, and you know that you split in half, and then this is the first half, left half, first half, we can say second half. Then it works with the first half again, and then what it does, it again makes another split. This is split only one element, so it does not need to do anything. So then it goes to the second part half, and the second sub part, and then what does it do? It split again. So then after this split, we will get only a single element list, right? This is a single element sub list, this is a single element sub list, and this is a single element sub list. And then what we will get over here, so whenever we find we get this single element sub list here, right? So then we will move to the right, the subset, okay, the right sub list. So then here, then again this sub list will be splitted again, and then this one will be splitted again, and then we will get like this sub list splitted into a single element, right? So this is a single sub list, sub array, this is another sub array, this is a sub array, this, and then we will move to here, and then it will be splitted again, and we will get 3 this part. So each of these are internally a single element list or single element array, right? So how many array, single element array? We got 1 2 3 4 5 6 7 here, that means 6 7, that means n is 7, right? So now the next part is to compare and merge, okay? And then so the compare and merge, so this comparison will be happen, so between two elements, right? So that this is a single element, so there is no comparison, it will come over here. So and then these are two elements, the comparison will go quickly in constant time or linear time, okay? So then 7 will come first, since 7 is smaller. So then and then again, now this list is sorted and this list is sorted. So then this part, okay, will come at the beginning, okay? So and then this part will go at the end. So we got it. So this up, so we started from here, and then we got a sorted, sublist, right? So now similarly, so these two will be compared, and then since 90 is less than 20, so there is no change, and then there will be a swapping over here. There will be a swapping here, right? So there will be swapping over here, and so then later, so when we merge, then what will happen? So this part, so elements of this and this will, this subpart and this subpart will be compared internally, and it will be solved. So 8, then 90, then we got 100, and then we got another sublist, and then again, so by merging these two we will finally get this. Right, so this will be a sorted list, sorted array. And how do we get it? We get through divide and conquer method, and in our next lecture, next week, we will see that how the divide and conquer method works. Okay, so its final part or dominant part is the merging, so this is called merge sort algorithm. So you see the merge sort algorithm is so far is known as one of the efficient sorting algorithms. Almost all sorting algorithms take n squared, big O n squared time complexity, but merge sort it takes n log n, because so here we will see how does it how that. Okay, so this is the intuitive display of how the merge sort algorithm work. So you can go through this slide and then try to understand how this happen. Okay, and then the main part. So main part is that here. Okay, so the merging part will merge n element, and then this will be done linearly, right? So if we come over here, so linearly, so that part will take theta n time. Okay, and then let's if we analyze now, if we analyze this algorithm, so okay, so what happens over here, so this is so my merge sort algorithm. So here this is n equal to 1, so this is, it will take every one thing is that every instruction or statement in a program takes some time to be executed, right? So but if the instruction is single instruction, is a simple instruction, then we consider that it takes a constant time. So then we say theta n, this is the 1, theta 1 is the constant time. We don't know yet, so that how the constant time maybe so maybe a few millisecond, 1 microsecond, 1 nanosecond, whatever it is. Okay, but it is a constant term. Okay, and then we recursively every time we recursively split the list into halves, right? So into halves, that means, so then we how many halves we do have? 2 halves, right? And then every time we split n by 2, so then complexity will be splitted by n by 2. And then for merging part we have theta n, right? So then total complexity will be 2 skips. This is an this is constant. Okay, so this part plus, okay, so so this part plus and this part. Okay, so the total complexity is considered as n log n. Why do we have log n? Because every time it is splitting by half, right, over here. So that is, so if an algorithm itself does only this part, splitting half, then its complexity will log n, log base 2 n, like log base 2 n. Okay, and this part will take n, right? So the recursive merge sort algorithm, it has total time complexity will be theta 1 if n equal to 1. That means only one element in a list. right? So if there is only one element released, there is nothing to sort, that is, it will take constant time, no matter how large or how big or whatever is our element is. So if an array here has only one element 5, so there is nothing to sort. If the element is 50, there is nothing to sort. Okay, if the element is 500, nothing to sort, and it is will every time it will take a constant time. Okay, and then the dominating part will be, so then it will be this part, right? The dominating part will be this part. So since for a large n, so this starting part is the this is called base part. Okay, so this base. For recursive algorithm, we know that there is a base case. This is the base case. Okay, so the recursive algorithm, every recursive algorithm has a base case, right? So this is the base. So for the base case, we say this is Tn equal to theta 1. Okay, and we consider that this is pretty same for the small n, but when it has no effect on the asymptotic recursive solution, actually what happens, it has when n is a large number, it's not equal greater than 1, but it's large, pretty large. Okay, and has effect. So what is the effect will be over here? So this part has effect. This is the, you remember, this is the merging part, and this is the splitting part, right? So the splitting part, so total recursive time will be 2 since there is 2 splitting, 2 parts, 2n tn by 2 plus cn, that means a constant of n terms will be 2 marks, right? So as we see that cn, that is in so that original number, it is splitting half every time, it is splitting half, and at the end we will get a single element, right, all the way in as a leaf part. So that is the constant. Okay, so now, so height, how many times it will be splitting? 1, 2, 3, like the splitting will be log n. Okay, then so how many elements it has? It has n elements, right? And if one element takes n times constant time, so that's cn total time. And then how many elements it will have? Okay, same times n by 2 plus n by 2, that is cn. And how many elements it has? All the 4 splits, but it is total is cn, right? And then how many elements it will have? It will how much time it will take? So it will have n splitted or single element list, right? So the total will be still again a cn, constant number. Okay, so these are the leaf parts. So as we saw that when we go to reach to the leaf, then we start, what do we start? We start merging, right? So now the total will be, so if we add up, so how many of cn we do have here? So we have 1 cn here, 2 cn, 3 sorry, and then actually how many will we have here? This is the length, right? That means if we say this is a rectangle, so then this is we consider as a rectangle. If we consider as a rectangle, so like this has cn times, right? This is the width is cn, and height, and this is height, right? How much is height? Is log 2n. Okay, so then what is the area, total area of a rectangle? Is width or length times height, right? So then total time will be n log n. So it's base 2. Okay, the total time will be n log n. So remember that. How do you get it? So if it is a rectangle, so this size has every steps it has cn. So this has cn and this has log n. So this side is log n. So the total will be theta of n log n. Okay, so here n cn log n, that means actually it was total time would be theta of cn log n. So this has cn and this has log n. So total will be cn times theta of cn times log n, since c is a constant. So compared to n, what is a very large n, c is this constant is ignorable, so we say n log n. Okay, so now we can compare that, we can conclude that compared to the insertion sort algorithm that takes theta n squared comparison, or we say operations, the merge sort algorithm takes n log n. Okay, for now, for a large n, which one is better? For a small n, this may be better, but for a large n, this is always effective. So merge sort algorithm beats the insertion sort algorithm for a large n, especially if people say sometimes 30 or something, more than 30 or something. Okay, so in our next lecture we will discuss asymptotic notations. That means we found here theta, okay, theta, and then other, there is big O, and then omega notation that we use for upper bound, lower bound, and theta is called for tight bound. Okay, we will discuss this in our next lecture. But meanwhile, before we go to our next lecture, I would like you to go through our D2L page, and you see then in our D2L page I have started organizing my lecture slides and videos. So this lecture, the week 1 has actually only 2 lectures, and the welcome is a welcome lecture, and then welcome video and welcome video, and then lecture 1 part 1, and this is the part 2. That this video is part 2. I will be uploading here soon, so please start watching. And that what is to say. So okay, since the first week has still a drop time, so I have not given any assignment or quiz in week 1. But one thing that we have getting know about you, so I am making it visible to you. So please open it, and then this is the some silly questions to ask you, and email me. Okay, when you complete it, just email me. Okay, and then we will have some quizzes, not maybe quiz and an assignment or quiz, that will be ending by the next weekend. Okay, that will be due by next weekend. Okay, and I will upload the quiz or assignment over here by this week, and I will give you this weekend, coming weekend. Okay, to submit it. So okay, so meanwhile I like you, please open the book, start here, and so this is our book, right, textbook. So please go to this, download this book, and then read, start reading chapter 1 at least. Okay, chapter 1 and chapter 2 we will go to in our next lecture. Okay, and thank you so much, and I believe gradually we will be organized in this course, and don't worry, you will learn something new a lot from this course. Okay, thank you so much. Bye.